So we've gone through, periodic signals, even and odd signals. Now, the next one is also, really essential to our discussions later on, which is the complex exponential signals, right? The class of complex exponential signals. Okay. So what are complex exponential signals? Okay. So in continuous time, a complex exponential signal can be written in this form, right? Basically, a constant c times exponential a times t, where t is time. Okay. And in general, the c and a can be both complex numbers. So c and a here, in general, can be complex numbers. Now, this complex exponential signal can behave differently depending on your choice of c and a. Okay. Now, suppose you choose c and a to both be real. In this case, we have a real exponential. Okay? Now, suppose that you have c greater than 0, right? So with c greater than 0, this real exponential will be a growing exponential if a is positive, and will be a decaying exponential if a is negative, right? So if a is positive, this will grow as time t increases exponentially. And if a is less than 0, okay, it will decay as t increases, also, exponentially. So you see this in a lot of places, right? So you will see such an exponential growth if you're looking at, for example, chain reactions of these atomic explosions or chemical reactions, right? And you will see this exponential decay in, for example, the discharging of your RC circuit. Now, this is the simplest type of, exponential signal, which is obtained when you choose c and a both to be real. Okay. Now, another common type is when you choose a, the exponent a, to be pure imaginary. Okay. So suppose we choose c to be a constant, let's say 1, and let a be this pure imaginary number, right? So we write it as j times omega naught, okay? So if you plug j omega naught inside here, then what you get is actually a periodic complex exponential signal, okay? Now, why is this periodic? Okay, why is this periodic? It's because if you take e to the j omega naught and e to the j omega naught of t plus capital T, right? You can show that you would be able to find some period, capital T, such that this becomes equal to the original signal, e to the j omega naught t. Okay? So indeed, if you split this up, you can write this as e to the j omega naught t times e to the j omega naught capital T. And when would this be equal to the original signal, e to the j omega naught t? Okay? So it would be equal to, the original signal e to the j omega naught t if omega naught times capital T is an integer multiple of 2 pi. Okay? So this would be equal to 1 for omega naught t that is some integer multiple of 2 pi. Okay? or that t is an integer multiple of 2 pi over omega naught. And because this signal repeats itself, okay, for any integer multiple of 2 pi over omega naught, okay, therefore the smallest period you can find is when m is equal to 1, and therefore 2 pi over omega naught is the fundamental period. Now this periodic complex exponential is closely related to a sinusoidal signal as given here. Okay? So as we're all familiar with, a sinusoidal signal, right, either sine or cosine, has a certain, oscillates at a certain frequency, let's say omega naught, sometimes offset by a phase phi. Okay? So a plot of this sinusoid is given here. Okay. So if phi is equal to 0, then at time 0, cosine should be 1, right? So if phi is equal to 0, then you have a peak at time 0. But because of this time shift, because of this phase shift, therefore at time 0, what you observe is cosine phi. So when there is this phase shift phi, right, at time 0, the point you observe is cosine phi instead of the peak. Okay? So the peak is offset due to this phase shift. Okay? But regardless of the phase shift, this sinusoid is always periodic. Right? It's always periodic. And the fundamental period is, again, 2 pi over omega naught, similar to this. So by convention, here we're going to refer to the phase using radians as the unit, okay? And if we think of time as seconds, then this frequency would be in radians per second. So for a sinusoid, it goes through one cycle, okay, after 2 pi radians. Now some people, in some other textbooks, they like to, use define frequency in terms of number of cycles per second. Okay, so in that case, you would write omega naught as 2 pi f naught, where you view this f naught as the frequency in terms of cycles per second. Okay, or hertz for short. Okay. So throughout this textbook, we're going to use omega naught, right? We're going to measure frequency in terms of radians per second, but just to let you know that some other textbooks would prefer to use cycles per second instead. Okay. This basically differs by 2 pi. Now, how is this complex exponential related to the sinusoid? Okay. So this is mainly due to the Euler relation, right? Euler's relation. So Euler's relation tells us that, Euler's relation tells us that this e to the j times a phase, okay, omega naught t, can be written as cosine omega naught t plus j sine omega naught t. Okay? So if you plot this out on a complex plane, this is basically a vector at the unit circle. Okay? So if this is the real domain and this is the imaginary domain, okay, then e to the j omega naught t is like a vector, okay, on the unit circle. And this is because e to the j omega naught t has the magnitude 1 and has an angle or phase of omega naught t. So if you project this point onto the real axis, you get here cosine omega naught t, right? And if you project this onto the imaginary axis, you get sine omega naught t. Okay? So e to the j omega naught t is equal to cosine omega naught t in the real axis and sine omega naught t on the imaginary axis. Okay? So, right. So you go a full cycle, okay? All right, so as time increases, as this time increases, this phase starts to increase, right? So as time increases, your phase starts to increase. And you go a full circle after 2 pi, okay? So as t increases, you start to, the phase starts to increase, and you go a full circle after 2 pi, okay? Right. So this is, you can also use this to sort of understand why this signal is periodic, okay? Is periodic if omega naught, is periodic with period t when t times omega naught is equal to an integer multiple of 2 pi. Because, this means that it comes back to the same point m times after time capital T. So again, right, okay, so this is going to be a very important function that we will use throughout the course, okay? So this periodic complex exponential e to the j omega naught t is essentially this vector on the unit circle, okay, that, that goes in one full cycle every time omega naught t is 2 pi, okay? Now, if omega naught is larger, then this goes around faster, right? If omega naught is smaller, then it goes around slower over time, okay? So with a higher frequency, you rotate faster. With a lower frequency, you rotate slower, okay? Now later on, we will also encounter frequencies that are negative, okay? So what happens if omega naught is negative? So when omega naught is negative, you turn in the opposite direction, right? But depending on the magnitude of omega naught, it still determines how fast you rotate around this unit circle, okay? So this is sort of, what it means to have a positive and a negative frequency, okay? It's basically the same, determines the same speed of rotation, it's just in different directions, okay? All right. So with this Euler's relation, which you will use repeatedly throughout this class, you will also be able to write any sinusoid as a linear combination of these complex exponentials, okay? So in particular, cosine of this angle here is equal to 1/2 e to the j of this phase plus 1/2 e to the minus j of the same phase, okay? And you can easily check that this is true because by Euler's formula, Euler's relation, this complex exponential you can write as cosine omega naught t plus phi plus j sine omega naught t plus phi, okay? And for this part, you have cosine minus omega naught t minus phi plus j sine minus omega naught t minus phi. Now we know that cosine is a even function. So if I bring the negative outside, nothing changes. Okay, and sine is an odd function. So sine of minus this thing inside is equal to minus sine of omega naught t plus phi. Okay? So you can see that when you add the two together, the sine cancels out. The cosine plus cosine becomes 2 cosine. 2 cancels out with the 2 here, and therefore you get the original formula. Okay? Now, alternatively, you can see that, this, okay, is actually this part here times 2, right? Okay? So we can actually write this as, 2a, the real part of e to the j phi, e to the j omega naught t. So a cosine can be expressed, wait a minute, I think, oh, sorry. So there shouldn't be a 2 here. Okay, sorry. Right, so cosine is just the real part of this, right? So I can write this as a times cosine, which is the real part of this, okay? All right, now similarly for sine, right, suppose you have a sinusoid that you write as a sine omega naught t plus phi, okay? By the same reasoning, you can write this as a over 2j e to the j phi e to the j omega naught t minus a over 2j e to the minus j phi e to the minus j omega naught t. Okay? And you can check by substituting this inside here. Okay? And similarly, you can write this as a, the imaginary part of e to the j phi e to the j omega naught t. Okay? Because sine is indeed the imaginary part of this complex exponential. So as we mentioned, right, a fundamental period, right, all these complex, pure imaginary complex exponential, or these sinusoids here, right, are periodic, and they have a fundamental frequency, fundamental period of 2 pi over omega naught. Okay? Now, if you take, 2 pi over t naught, right, if you flip this around, then you get this omega naught, which we call the fundamental frequency. Okay. So the fundamental period is the smallest period for which you can observe this periodic behavior. Okay. And the fundamental frequency omega naught is the smallest frequency that you can have in order to have a period of t naught. Okay? So certainly if you increase the fundamental frequency by 2 times, you may still have a period of t naught, but that would no longer be the fundamental period. Okay? So the fundamental frequency determines fundamentally how fast this sinusoid varies over time. Okay? So here we have an example of 3 sinusoids with different fundamental frequencies. Okay? So this is omega, the top one is omega 1. We assume is greater than omega 2 and greater than omega 3. Okay? So you can see that with the larger fundamental frequency, right, the sinusoid varies faster than those with smaller fundamental frequencies. So I know that my time is up, but let me talk about one more thing for you to think about over the weekend. So here we start out with a fixed omega naught, right? So we say that if we choose A equal to j omega naught, then we have a periodic signal with period that is 2 pi over omega naught. Okay? Now let's suppose that you say that this complex exponential is periodic with period t naught. Okay? So when can a complex exponential be periodic with period t naught? Okay. So if you want it to be periodic with period t naught, then this means that x of t should be equal to x of t plus t naught, right? So if you plug in x of t inside, this means that e to the j omega t should be equal to e to the j omega t times e to the j omega t naught. Okay? And in order for this to be true, e to the j omega t naught must be equal to 1. And this can only be true if omega t naught is equal to an integer multiple of 2 pi. Okay? So this can be periodic with period t naught, okay, if omega t naught is equal to 2 pi, an integer multiple of 2 pi. Okay? Or in other words, if you move t naught to the other side, this means that omega must be an integer multiple of 2 pi over t naught. Okay? And let's define 2 pi over t naught as omega naught. Okay? We define 2 pi over t naught as omega naught. Okay. So what does this imply? Okay. What does this imply? You want to go, right? Okay. So what does this imply? So when you have a signal with frequency, okay, omega naught equal to 2 pi over t naught, this means that over a period of t naught, you observe one cycle of the sinusoid. So if you continue to draw this sinusoid, you can see that it is periodic with period t naught. Okay? Now, if I increase the frequency by 2 times, right? So here, my frequency is omega naught. Okay? So suppose I choose a frequency of 2 times omega naught, then I should have 2 cycles within t naught. Now, if I choose a frequency of 3 omega naught, then I have 3 cycles within t naught. Okay? So the frequency continues to increase, right? It varies faster and faster, but they are all still periodic with period t naught. Okay? Now, all of these sinusoids that are periodic with period t naught are said to be harmonically related. Okay? Are said to be harmonically related. And you would observe that, in a lot in, let's say, in music instruments. So suppose that you're looking at a string instrument where you, tie the 2 ends, right? Something like this on the next slide, where you have, fixed points on 2 ends. Then when you draw your bow, right, you see oscillations of the string that actually takes on these sinusoids that are harmonically related, okay? And sets of harmonically related sinusoids have a significance in our study, okay? So let me stop here, and we'll go through this again next week.